Physics, part 199. If, however, the electron absorbs energy, perhaps being heated or by collision with another electron, it may be promoted to a higher energy level. The energy absorbed is exactly equal to the difference in energy of the two levels. Under these conditions, the atom is described as being in an excited state. This is illustrated in our figure as we find it here. An excited atom is unstable. After a short time, the excited electron will return to a lower level. To achieve this, electron must lose energy. It does so by emitting a photon of electromagnetic radiation, as illustrated in the figure. The energy of HF and of the photon is given by HF is equal to E2 minus E1. Where E2 is the energy of the higher level and E1 is that of the lower level, and H is the Planck constant using the relation between the speed of c of light, frequency f, and wavelength lambda. The wavelength of the emitted radiation is given by lambda is equal to hc over delta E, where delta E is equal to E2 minus E1. This movement of an electron between energy levels is called electron transition. Note that the larger energy of transition, the higher the frequency and the shorter the wavelength, the emitted radiation. Note that this downward transition results in the emission of a photon. The atom can be raised to an excited state by the absorption of photon. But the photon must have just the right energy corresponding to the difference in energy of excited state and initial state. So a downward transition corresponds to the photon emission and an upward transition to photon absorption. Spectroscopy. The figure shows some of the possible transition that might take place when electrons in an excited atom return to lower energy levels. Each of the transition results in the emission of a photon with a particular wavelength. For example, the transition from E4 to E1 results in light with the highest frequency and the shortest wavelength. On the other hand, the transition from E4 to E3 gives the lowest frequency and the longest wavelength. Because all elements have different energy levels, the energy differences are unique to each element. Consequently, each element produces a different and characteristic line spectrum. Spectra can be used to identify the presence of a particular element. The line spectrum of mercury is shown in the figure. The study of spectra is called spectroscopy, and the instruments used to measure the wavelengths of the spectra are called spectrometers. Spectrometers, for accurate measurement of the wavelength, make use of the different gratings to disperse the light. Continuous spectra. When the light emitted by isolated atoms, such as those in the low-pressure gases, produce line spectra, the light emitted by atoms in a solid, liquid, or gas at high pressure produces continuous spectrum. This happens because of the proximity of the atoms to each other. Interaction between the atoms results in a broadening of the electron energy levels. Consequently, a transition of a wide range of magnitudes of energies are possible, and light of a broad spread of wavelengths may be emitted. This is seen as a continuous spectrum. Absorption spectra. If white light passes through a low-pressure gas and the spectrum of the white light is then analyzed, it is found that the light of certain wavelength is missing.